Thank you. All right. Good morning, everyone. Welcome to another session of our bi-weekly seminar series at Southern Illinois University, Carbondale. Today, we have with us Dr. Milad Roohi. He's an assistant professor in the Durham School of Architectural Engineering and Construction at the University of Nebraska-Lincoln. He also serves as the College Engineering Teaching Fellow, and he's the director of the Smart Resilient Infrastructure and Urban Systems Lab. Before he was at UNL, he was a senior scientist at Aeon's Impact Forecasting R&D Center of Excellence, and he did his postdoc at the NIST-funded Center for Risk-Based Community Resilience Planning at the Colorado State University. He received his PhD in civil engineering from the University of Vermont, and he works at the intersection of infrastructure resilience, structural dynamics, structural health monitoring, and community engagement. And he has been doing some excellent, exciting research over the last few years. And we look forward to hearing all about that work from Dr. Roohi. So Milad, please take over from here. But before you start, the audience, if you have any questions, please leave them in the chat, and Dr. Roohi will address all your questions at the end of the talk. Thank you. Over to you, Milad.
Thanks so much. It's an absolute pleasure to have this opportunity. I appreciate Dr. Sen's invite and everyone's. I see Dr. Khalil Razo. He's a great colleague of mine. I see Dr. Jay Pockets. He's a senior faculty in my department. Thanks so much. So I'm going to share my screen. Hopefully we are not going to have an issue. Looks good.
Full screen. Yeah, there you go. Perfect.
Perfect. Thanks so much. So today I'm so excited to discuss our research and present on engineering future resilience through co-creation. So today I'm going to discuss our research mostly on seismic resilience and tornado resilience. We are going to talk about integrated models of physical systems chained by socioeconomic models, and understand how we can leverage community engagement to enhance resilience of our communities. But first, to motivate my presentation, so I'm going to show you this really interesting plot from Aeon, which was my former employer, that basically summarizes the global economic losses from 2023. So in this plot, you can see some of the major events that has happened all around the globe, including in the United States. So you can see the economic losses based on the estimates from Aeon sums up to about $380 billion. But what is interesting to see is that this is about 22% above the 21st century average. And also in terms of the insured losses, we see the numbers aggregate to $118 billion, and this is about 31% above 21st century average. So one of the major drivers of this loss was the earthquake that happened in Turkey-Syria border. So it contributed about $92 billion. But also thinking about the history, so we have had various events that has contributed to development of our modern codes. And I wanted to show you this slide specifically about the type of earthquakes that we have experienced in Western United States. So in Southern California, back in 1933, we had Long Beach earthquake. So this event highlighted the importance of design regulations and building codes. And since then, there was new codes that, as part of the Field Act, so we introduced seismic design into our structural codes. Later in 1971, we had San Fernando earthquake, and this event specifically highlighted the importance of critical infrastructure. For example, utility systems, gas network, water distribution networks. And you can see some of the damage that has been documented in terms of the damage that bridges experience. This is an example of a hospital, and also this is one example of a dam that experienced seismic damage. And since then, there has been developments in terms of standards such as ASCE 7, and also updates to hospital design and retrofitting guidelines. Later on, back in 1994, we had Northridge earthquake, which was a major event back at the time. And it highlighted the importance of understanding post-event functionality and the time that it takes for our infrastructure to recover from this type of events. So after this event, we had major revisions to evaluation and retrofit guidelines. For example, we had an updated version of FEMA guideline, FEMA 356. And also one of the important contribution at the time was the emergence of performance-based earthquake engineering framework that I'm going to briefly discuss today, and also introduction of functional recovery as part of design goals, which is one of the major focus areas of US government. And also, obviously, we are expecting to experience big earthquakes in the coming years, coming decades. So I've included this USGS seismic hazard map, so you can see some of those areas that they are highly likely to experience major events. For example, in the West Coast, we have Oregon, Washington, that is basically a subduction zone that can experience major earthquakes in the order of 7 above to 8, 9 even, and also tsunamis. So we have Southern California, we have Wasatch Fault, which is basically the area, Utah, Idaho, and also we have New Madrid zone, Tennessee. So these are some of the regions in the United States that they are prone to major events. And also if we look at the recent years, for example, back in 2020, we had a magnitude 5.7 event which occurred in Salt Lake City, Utah. So in 2024, a few months ago, if you remember, this is back in December, so we had a major earthquake 7, and there were warnings triggered for tsunami in Northern California. But fortunately, we didn't have this tsunami. And more recently, 4 days ago, we had this 2025 magnitude 5.2, which was 11 miles from San Diego. So basically, this shows it's only a matter of time before the United States and also communities worldwide to face similar challenges and manage post-event situation in disasters. So to address this problem, the concept of community resilience has been introduced in the past 2 decades. And the idea is to understand how we can improve our community resilience by improving the ability to prepare for and adapt to changing conditions and withstand and recover rapidly from disruptions. So this includes natural hazards, attacks, accidents. And here I have one plot to basically explain what we mean by community resilience. So imagine this is a community that has its physical systems, socioeconomic systems. So before an event, so we have an initial level of functionality. Once a disruption such as an earthquake, tornado, flood happens within our community, so the infrastructure experiences loss of functionality. And then we need to go through this process of recovery, rebuilding, and restoration. So the area that I have highlighted here, it basically shows the total loss experienced by the community due to that initial loss of functionality and also that time to full recovery. And by resilience, we are interested to understand how we can decrease the total amount of loss, which is due to that initial loss of functionality and also time to full recovery. So when we discuss community resilience, a resilient community may have different characteristics. So here I have included 4 key characteristics that we expect from a resilient community. So the first one is understanding and recognizing the type of natural hazards that we expect in our community. So the community at risk needs to have the knowledge, systems, and tools in the place to provide warning in advance. We need to make sure that we can keep our individuals safe if they are there at their home, if they are at work. And also we need to make sure that our community would experience minimum disruption to life and economy after a hazard event. And when we discuss functionality, it's important to define what we mean by functional recovery. So functional recovery depends on the extent of damage and repairs and the ability to resume operations, and it is usually measured in relative to the baseline pre-event. So here I have included 3 examples of functional recovery curves depending on the class of the building in terms of the risk category of building, for example, critical, commercial, residential. We may have different expectation in terms of functional recovery post-event. For example, here you see, for example, for critical one, we may need to have continuous functionality and achieving full function as soon as possible. But for example, for a residential building, we may be able to tolerate a higher level of functional recovery. So depending on what is the goal for different type of systems, we need to be specific in defining this concept. So this is a really interesting plot that was recently released by National Institute of Standard and Technology to basically differentiate our current approach based on life safety design, as you can see in this plot at the bottom. So our current codes, they achieve moderate damage following major events. Then we need to go through the repair planning, and a few weeks or months, we may have ongoing repairs. So now the idea is if we can switch and change our design guidelines to design for functional recovery, for example, if we want to achieve 2 months target recovery. So now if you compare in the post-event, immediate damage is minor damage compared to that moderate. And then in 2 months, we have achieved functional recovery. So you can see the businesses are open, the occupants are back at their houses. And then also in long term, we can achieve full recovery in advance compared to the life safety design. So we are not there yet. So the idea is to understand how we can update our design codes to achieve functional recovery in our community. So to show you why this is important, so I thought this might be interesting to see what happened during the Turkey earthquake that I briefly mentioned earlier. So here you can see a map of Turkey, Syria, and this area that you can see that have been highlighted, it's Hatay. So Hatay is the southern Turkish province, and it was the region that was affected by 3 earthquakes in sequence. So this is a video from Guardian that basically compares the pre-event and post-event situation in the community. So you can see extensive damage to structural systems. So these are mostly mid-rise buildings that experience, you can see some of them that they have experienced collapse. So this is another view. So this was a major tragedy for Turkey and specifically for Hatay. So I had the opportunity to visit Hatay 6 months after the event, and we focused on the hospital network to understand what was post-event functionality of the hospital network. So in this plot, you can see the epicenter of 3 earthquakes, 6.3, 7.8, and 7.5 that happened back in 2023. So in these dots represent the bed capacity for different hospitals within the network. And then we have 2 types of hospitals, private and state. So we had the opportunity to visit most of these hospitals. So here is one of the examples. So we visited Dortyol Devlet Hastanesi, DSH. So this was constructed back in 2019. What is really interesting about this building is it is equipped with base isolators. So that was one of the reasons that the building was able to reduce the base excitation applied to the system. And immediately after the event, the building did not experience structural damage, and it was fully functional to the public. This was another hospital, Mustafa Kemal University Hastanesi. It's a Mustafa Kemal University hospital. So you can see even 6 months after the event, there were some repairs underway, and the building was partially functional. And this was the most interesting one, I would say. So back in 2017, this was a national project to build a hospital with more than 1,000 bed capacity. So you can see it's a reinforced concrete, modern design. So you can see different views of the building, 1,050 beds. And here are some pictures that I took during my visit. So you can see there were extensive damage to structural systems, non-structural systems. So you can see the ceilings, the foundation, and the building was non-functional immediately after the event. Even 6 months after the event, there were plans to demolish the building and rebuild a hospital. So we were able to put all the data that we collected in the aftermath of this event. And then now in this plot, you can see the hospital network capacity immediately after the event that dropped from 100% to about 31%. After the third earthquake, it dropped to about 14%. 3 months recovery, 26. 6 months recovery, about 64. And even 1 year after the event, the estimate shows that the hospital network recovered to about 83%. So now if we take this area above this curve as a measure of the losses experienced by the community. So the question is how we can address this challenge. So this brings me to this idea of co-creating resilience. So in the past 2 decades, extensive research has been occurred in the United States and all around the globe to understand how we can improve and enhance functional recovery and resilience of our communities. So based on this research and extensive work with communities, we have realized that improving resilience, it is no longer a top-down engineering challenge. So at today's world, if we want to address this challenge, we need to develop multidimensional processes through co-creation and engaging with communities. We bring engineers, planners, policymakers, and communities to collaboratively shape the future of our resilience. So one of the major efforts in this space in the past decade has been by National Institute of Standards and Technology. So they released a playbook, which is basically a community resilience planning guide for US communities that has 6 qualitative steps. So the first step starts with forming a collaborative team. So we need to identify our leader for our resilience planning, identify our team members, our key stakeholders. So once we are done with the first step, so the second step is to understand our situation. So this is not only in terms of our built environment, but also in terms of our social dimensions. So we need to first characterize our social functions and dependencies. We need to identify how our social dimensions are supported by our built environment. We need to identify our contacts. We need to understand our built environment vulnerabilities. We need to understand who are the agents that they are responsible to manage our infrastructure. And then we need to cluster our systems and connect our social functions to our built environment to understand the dependencies. So as soon as we have good understanding of our hazards, vulnerabilities, exposure, and these dependencies, so then the community needs to determine their goals and objectives. So we need to first develop long-term goals for our resilience planning. We need to establish our performance goals. We need to look at the type of hazards, scenarios that we expect in our community, develop models, metrics that basically provide the anticipated performance, summarize the result, and use this information to develop a plan. So to develop this plan, we need to identify the resilience gaps. So what is our baseline currently, and then what is our goal? So that goal compared to our current baseline would give us an analysis in terms of the current gap. Then we need to identify solutions and develop implementation strategy. Then we need to prepare, review, receive the approvals, and then go through the implementation process. So this process was developed as part of long-term collaboration between NIST with more than 250 stakeholders across different disciplines. And also another effort that I believe it's important to discuss is ASCE Infrastructure Division IRD framework for multidimensional resilience. So in this plot, you can see we have 3 different dimensions to characterize resilience. The first dimension is hazard. So you can see depending on the region of interest, the community of interest, we may have different type of hazards. In terms of the second dimension, which is the system dimension, you can see we can include different type of infrastructure systems, transportation, buildings, water, power, communication, etc. And in the third dimension, which is our event cycle, we have planning, mitigation, pre-event, response during the event, and also recovery and rebuild post-event. So now if I take, let's say, for example, buildings subject to flood in the planning stage, so that's going to give us a cube. So inside this cube, so you can imagine we have different dimensions of resilience, and we can develop models that can help us to identify the vulnerabilities, strengths of our building stock, let's say subject to the flood. But if we want to have a comprehensive understanding of our resilience, we need to be able to characterize these three dimensions by accounting for risk and uncertainty. There are many aspects that goes into this process. For example, we need to evaluate the dependencies. We need to collect data. We need to look at our policies. There are various aspects related to social science, economic science. There are aspects related to decision making, educating our workforce, educating our communities. And then also, in the past few years, there has been also efforts by National Institute of Standards and Technology and also ASCE to understand what are the challenges and needs to identify how we can address multidimensional resilience. So here I have listed three of the major challenges that we are facing. The first one is to develop standard metrics to quantify the performance and functionality of physical systems, socioeconomic systems before and following natural hazards. The second challenge that we are facing is we need to identify what are the data requirements, what type of data sources are available to quantify resilience metrics. And ultimately, we need to develop methods that they can integrate, aggregate different type of data from different sources, and specifically multidisciplinary data to compute metrics that can inform our decisions and policy development. So one of the guiding principles to address this challenge is performance-based performance-based engineering and risk assessment methodology that was developed back in 2000. So performance-based engineering provides a probabilistic and modular evaluation of natural hazards and also their consequences. So we can use this concept for the purpose of design and also assessment of our systems. And it has three major components, starting with exposure, that we need to first characterize geolocation, construction material, if we are interested on buildings, number of stories, year construction, and occupancy type. Depending on the type of hazard of interest, we need to identify our region of interest, look into the frequency and intensity of the hazards, hazard parameters, and develop a model for the hazard of interest. Then the exposure and hazard information are passed to vulnerability module that basically takes the information in terms of the hazard and exposure, and we can develop different modes of different types of models depending on the accuracy and computational efforts of interest. For example, if we are interested to do high resolution analysis, we can develop high fidelity models such as finite element models. If we want to use reduced order models, we can rely on multi-degree of freedom, low fidelity models. And also, usually for risk assessment, we rely on fragility functions or damage functions. So these type of functions, usually they are in the form of log normal cumulative distribution function, CDF. And you can see each function characterize the probability of exceedance of different damage states, for example, light, moderate, extensive, given the demand parameter. So it could be in terms of intensity measure. For example, if it is flood, so that could be the flood scenario height in the location of your asset. If it is earthquake, that could be a parameter related to, for example, peak ground acceleration. So as soon as we have our exposure, hazard, and vulnerability model, we can perform damage analysis for an individual asset or an inventory of assets and estimate the distribution of damage and then perform loss assessment in terms of the loss that a building experienced due to structural damage and also non-structural damage. So this framework can be written using this three-dimensional integral. Those probabilities that you can see, they are probability distribution functions. So basically, we need to start with intensity measure by doing hazard analysis. Then we need to obtain engineering demand parameters given intensity measures. Then we need to estimate damage measures given our demand parameters. And ultimately, we need to estimate decision variable given damage measure. So if we solve this three-dimensional, very complex integral, we can characterize that probability of decision variable. But one of the challenges that performance-based engineering concept has, it lacks components related to multidisciplinary aspects and also understand how we can characterize interdependency between different systems, including infrastructure systems and also community systems. So for this, we need to first understand that here we are talking about a network of interdependent and interconnected physical and sometimes virtual systems that they rely on each other to function properly, efficiently, and effectively. So this can encompass different sectors in terms of transportation, energy, housing, telecommunication, healthcare, etc. But in addition to infrastructure systems that we just discussed, we also have the interdependency between our networked infrastructure with our social and economic systems. And we need to understand what would be the impact of failure, let's say, in a component of our interdependent system in the functionality and performance of the entire physical infrastructure, and also in terms of the performance and the impacts that this failure would have on our social and economic systems. And the question is how we can characterize this cascading failure by accounting for this interdependency between infrastructure, socioeconomic systems, and characterize the ability to recover following major events. So to address this need, in the past decade, as part of National Institute of Standards and Technology funded center on INCORE, which is Interdependent Networked Community Resilience Modeling Environment. So we had a 10-year effort to bring economists, social scientists, engineers, and computer scientists working closely with National Institute of Standards and Technology to develop a platform that can help us to conduct this type of analysis, characterize interdependencies, and quantify resilience. So INCORE was released 4 to 5 years ago, so it's available to the public and users that are interested to analyze and run scientific analysis to model the impacts of different types of hazards on communities and optimize their strategy to improve resilience. So here you can see some of the major features of INCORE. You can run individual hazards, you can run multiple hazards, perform long-term resilience assessment. We can characterize different type of systems, buildings, transportation, energy, communication, etc. We have advanced modules to model social systems, economic systems, and we can also develop optimization strategy to improve resilience. There has been efforts to develop multiple testbeds. Here are 5 examples, but we have extended to more than testbeds now. And also we have built partnerships to work with communities to develop real testbeds for US communities. So it is open source, it is multi-scale, it is hosted at NCSA, which is National Supercomputing Applications Center at the University of Illinois Urbana-Champaign. And this is the website that if you are interested to access the platform and also the guidelines. So obviously, there has been extensive efforts to develop models and modules within this platform. So I thought I'm going to just show you one example to give you an impression of what type of analysis we can do using INCORE. But this is not exhaustive. So there are various type of models that are available on our GitHub, and you can look at the modules and also examples on the website. So this is one example that we developed in collaboration with our colleagues at Colorado State University and Texas A&M. So first we started with developing a multidisciplinary framework to characterize community resilience subject to earthquakes. So this is an example of Memphis, Tennessee, in terms of buildings and electric power systems. So we were interested to collect multidisciplinary data in terms of the physical assets and also social and economic systems. The next step is in the framework is to do a spatial seismic hazard modeling to obtain the distribution of intensity measures in the region of interest. Then we develop interdependent infrastructure network model. So the approach that we use is we use directed graph in which each asset is characterized using a node and the dependencies are characterized using directed links. So here are the building stock, this is the bridge network, and this is the water distribution modeled as an interdependent network with electric power system. Then what we do is we run a fragility-based analysis by mapping our fragility functions depending on the characteristics of each one of these nodes. Then run physical damage analysis, quantify functionality metrics, and look into the restoration of the network. Ultimately, this information are passed to social and economic scientists to develop social and economic models for economic model, we rely on computable general equilibrium, which is CGE model, which is an advanced model that can account for the interdependencies between the building stock with economic sectors and characterize the shock to the economy and quantify metrics such as employment, impacts on household income, impacts on domestic output. And also in terms of the social model, we use a population dislocation module to develop metrics in terms of the impacts on the population by accounting for their demographics, their characteristics. And also, we can also bring measures, for example, to distinguish between renters and owners. And also, we have other type of social models available, for example, housing recovery models that can also look into that process to recover a housing. So I'm going to show you representative results from this analysis. So here we are modeling a magnitude 7.1 scenario earthquake. In the left side, you can see the estimates in terms of functionality of substations as part of our electric power network. So you can see the numbers are between 0 and 1. 0 means non-functional, 1 means functional. So you can see there are some substations that they are non-functional subject to this event. In the right side, you can see functionality 7 days after the event. As we expect substations to recover promptly, you can see in about 7 days or a week, most of those substations that they have recovered. Then we link our network system to our building structures and quantify probability of buildings to be functional by accounting for the performance of the building itself and also the utilities that they support the building function. We collaborated with Rice University to run analysis in terms of the transportation network. So now here you can see the bridge infrastructure in Shelby County. So the estimates here showing probability of damage state 3, which is extensive damage subject to that scenario event. In the right side, you can see now the time to full restoration in terms of months. And now we can take these trajectories and plot the functional recovery subject to the scenario event. So now we can see the bridge network 0 months after the event, 1 month after the event, and 2 months after the event that most of those links and nodes have recovered. And also we can pass this information to our socioeconomic colleagues to obtain estimates in terms of socioeconomic impacts. So now we can see what we get in terms of impacts on employment, social aspects such as economic aspects such as household income and also domestic output. But what is interesting is what would be the implication of this type of advanced resilience models in terms of mitigation, the impacts of natural hazards. So one of the efforts that we have had in the past two years was to understand how we can use this type of modeling framework to develop seismic mitigation to achieve community resilience goals. So we have extensive background and guidelines to retrofit a single structural system. But in this case, we are interested to understand how we can connect structural retrofit of individual buildings to broader resilience goals of the community. So now if we plot the functional recovery curve for the entire community, how we can reduce the losses through a seismic upgrade. So to address this, we integrated the framework that I discussed into an updated version of the framework that basically takes the multidisciplinary data, seismic hazard model, damage model, functionality model to first quantify multidisciplinary metrics. Then we develop multiple retrofit strategies and iteratively go through this process to do cost and benefit analysis to understand how much the retrofit would cost in the community level and what would be the improvement in terms of seismic resilience metrics. And as I mentioned previously, this is a multidisciplinary framework, so it is able to account for interdependency between different type of sectors from economic aspect with building structures, and then we can also model the interdependencies between our building inventory with our housing inventory by bringing a housing unit allocation that basically characterize the characteristics of the population as well. So one of the communities that is facing challenges with earthquakes is Salt Lake City, Utah. So the Salt Lake City, so this is a view of downtown Salt Lake City. So that's the capital. And then the community has about 1.18 million in terms of the population estimated based on 2020 US Census data, with about 284,000 buildings. SLC is located along Wasatch Fault. So you can see in this plot, it extends all the way from southern part of Idaho to central Utah. And these are some of the major events that has occurred in the past since 1850 to 2020. So you can see the size of the starburst shows the magnitude of events. So specifically, you can see a number of events were greater than 6.5. And the question is, so if the community is ready for such an event in the coming years. So as I mentioned earlier today, back in 2020, we had a earthquake magnitude 5.7 that had some minor to moderate damage to unreinforced masonry buildings. As you may know, this type of buildings, they pose significant risk to our communities. And even though the state of Utah has adopted codes that they do not allow construction of URMs, we still have more than 140,000 URMs in the state of Utah. So we started our planning efforts by getting engaged with the community officials and decision makers and stakeholders. So you can see we had a number of meetings in Salt Lake City in person to first identify, so what are the capabilities in terms of the budget, the resources available from the local government, the opportunities to pursue funding from US government. We discuss how we can leverage this type of modeling to make it useful and usable by their planners and engineers. And then we realized, so they are interested to run several scenarios that are consistent with the assessments that the working group on Utah earthquake probabilities has, which indicates that there is a 57% probability of one or more magnitude 6 or greater earthquake in the next 50 years. There is about 43% probability of one or more greater earthquake with magnitude 6.75. So we decided to initiate our analysis with running two events with magnitude 6.5 and 7.1. We looked into the characteristics of the faults. We looked into the past events. We looked into the data available in terms of the liquefaction susceptibility, which is a major concern for Salt Lake City. And then we were able to run our damage analysis, obtain the probability of exceedance for different limit states, slight, moderate, extensive, estimate probability of failure for different buildings within the community. Then we passed all this information to economic scientists, and then they defined two regions in the northern part of Salt Lake City, which we call Region A, and the southern part, Region B. So what we did, so we were able to quantify resilience metrics, for example, in terms of building functionality. Now you can see the pre-event condition, 6.5 and 7.1. So if we run this analysis by accounting for the dependency with electric power systems, now you can see the differences. So these are the metrics that we receive in terms of loss of function. So this is the baseline pre-event in terms of number of employments. Then you can see the drop. So this is a log scale plot. And then region A, region B. Then we also obtained household income metrics for both regions and also domestic supply. Now that we have this scenario simulated, we were interested to identify how we can mitigate these impacts. So for this, we considered seismic retrofit of URM buildings as an illustrative example. So first, we obtained fragility functions for retrofitted and non-retrofitted buildings that are consistent with the building stock that we have in Salt Lake City. Then we obtained data from FEMA BCA tool in terms of the costs that are basically estimates of the local cost to upgrade buildings, URM buildings. And then we used existing fragility curve from Jiang El Nashai as part of Mavis project. So first we started with creating 5 different cases of retrofit, case 1 to case number 5. So case one is about 25% out of retrofit. And then as we go from case one to case number 5, we increase the percentage of retrofit for URMs to 100%. So now we are able to rerun all this workflow and estimate the functionality metrics for physical infrastructure by accounting for dependencies, in this case, and buildings only at the top. So now you can see as we increase the functionality, as we retrofit more buildings, so obviously it's going to improve our functionality metrics. Then we pass this information to economic scientists to quantify employment impacts. Now you can see across those 5 cases, subject to 2 events, 2 different regions, we had the base value and also changes in terms of the employment. Then, so now that we have the baseline in characteristics, metrics, and also we have the upgraded metrics, so now we can start to do resilience gap analysis. So we can look into our baseline. We can define targets, for example, for building functionality. Let's say we are interested to achieve 90% functionality. For employment, let's say we want to limit the employment impact to less than 2%. So now what we can do is we can look into this different analysis, compare our target with the metrics that we get. And whenever we exceed the target, so that would be the optimized strategy to retrofit. Then we started to think about like how we can make this framework useful and usable for the community. So at the top, we have the in-core modeling approach. And at the bottom, we have the playbook that I discussed earlier. So we started to think about integrating our in-core modeling framework with the playbook to understand how we can develop a version of an interface that could be useful for the community. So this was our effort to create our first version of an interface. And then, so these are some screenshots that basically shows, so you can, for example, look at Salt Lake City in this case, different parts of the city. Then, so the interface allows you to zoom in, zoom out, look into different strategies, identify different type of systems that you have within your community. As soon as you decide on your retrofit strategy, you can use our retrofit strategy builder. So that's going to give you an estimate depending on what type of strategy you choose. You can have conditions. It shows the number of buildings. Then you can go through a process to run this interface, and it's going to basically give you the estimates in terms of the number of buildings that they are functional or non-functional, baseline, and retrofitted. And that's going to give you all these visualizations that can be used by the community. So I'm going to show you a video that basically shows how the
fact that we live on such dormant but potentially active fault lines in the city. There was always this notion of like one day a large earthquake might come. But then everyone's eyes were definitely wide open when we did have the earthquake in 2020. So as scary as that was, it's a good reminder and it's a good wake-up call to be prepared as much as we can here in Salt Lake City. And in our division, we administer the city's HUD funds for community development grant programs. But then we're very excited to have brought on the Fix the Bricks program, which is funded by FEMA.
The Fix the Bricks program is seismic retrofit for unreinforced masonry buildings. So brick buildings that were built before 1970s.
In an earthquake event, before it was reinforced, it would wiggle around and the roof would collapse. Walls would go in, walls would go out. And now when we're reinforcing it, we're kind of making it one structure so it wiggles.
The building stays intact so that the homeowners can escape the building in time to preserve life. If an earthquake does happen, that results in so many other potential risks, losing power, floods, no street access for emergency management to even get to those places. And the hope with using INCORE is it can show us exactly where that earthquake risk could happen.
INCORE can process several layers of data at a time. You can look at geographic data, you can look at geologic data like fault lines, liquefaction rates for soils, and then they can look at community resilience levels. So for example, we could put in data on hospitals and say, what would be the strain on hospitals after a disaster? compared to if a large number of houses collapsed or if we put the mitigation in place and fewer structures collapsed. NCORE also allows us to put demographic layers and say we want to look at factors like socioeconomic risk, race, ethnicity, income, and then historical disparities like redlining. And then let's also see which residents are least likely to be able to make these retrofits on their own, and then target the grants to reach the most vulnerable.
Using NCORE and seeing that data really shows us how much an earthquake can impact more than just the house, and really seeing it holistically.
With NCORE, we can get really granular. We can not just see the risk, but then also the recovery model, and then displacement models. How many people are going to need temporary shelter? How many people will be able to return to their homes in what period of time? And the NCORE team is able to take that and create a custom solution that allows you to get data to find the answers.
So in the interest of time, I'm going to stop the video there. So now what is happening is basically the community has access to this platform, all the data sets, the models, so they can look into the model, change the scenarios, they can make changes to different components, they can have their own consultants, engineers, and then so they can leverage this to basically submit applications to US government and possibly receive funding. And then so now it's going to help to produce metrics that are relevant for decision making. But I also want to briefly, so I'm not going to have time to cover all the slides, so I'm going to also briefly mention that we also look at multi-hazard in my lab. For example, tornadoes are a big concern for the state of Nebraska and also for the United States. So in the left side, you can see the tornado tracks. In the United States, usually we have about 1,000 to 1,300 tornadoes. Here is one plot that shows we have about 40 to 60 tornadoes in the state of Nebraska. This was a tornado that passed through my neighborhood. So this is where my PhD student Pramodit and I live. And we had a tornado that passed through our neighborhood. And even yesterday, we almost had a touchdown in downtown. So this was the tornado that occurred in Nebraska in April 26, 2024. It devastated our community. You can see the extensive damage to our buildings. And then that's been one of the reasons that we've started also to look into validating tornado resilience models that are available from the literature. So first we started with developing a framework that basically takes exposure model for in this case, tornado resilience analysis, hazard model, developing damage analysis based on fragility functions for tornadoes, obtain metrics, and compare with the post-event reconnaissance data that is available from US communities. First, we started with mapping our damage states with the field damage states. So this table shows how we can characterize component level, extent of damage and map it to system level damage, which is assessed during reconnaissance. And now we can use this for the purpose of validation. So we developed multiple test beds for different communities that have been impacted by tornadoes. For example, here you can see an example of a tornado that happened in Dallas. And then we also have Nashville tornado. And then, so my PhD student was able to develop a resilience model to look into the damage states that we obtained from our models and compare with the field estimates. So now you can see the comparison between the model estimate with the field estimate. So now we can take this information to understand how useful are our models to characterize the tornado damage in our communities. So this is a confusion matrix that we recently developed for these 5 test beds. So in the x-axis, you can see the field damage states, and in the y-axis, you can see the model damage states. So far we are saying, so in the best case scenario, we are expecting to have a diagonal confusion matrix that basically the field damage states are consistent with the model damage states. But as you can see, there are off-diagonal terms that basically shows in some cases we are overestimating or underestimating the tornado impact. So my PhD student is focused on understanding how we can address this shortcoming to improve our models. Also, we have received a project funded from National Science Foundation, Civic Innovation Challenge, to work with Omaha tribes to understand how we can leverage this modeling and collaborate with our aviation department and computer science department to develop a framework to address wind resilience in Omaha tribes. I'm also collaborating with Nebraska Department of Transportation to implement a flood resilience framework. So in this case, we are interested to look into interdependencies between our bridge and transportation network with our building inventory, develop flood hazard models, network modeling, and go through process of resilience modeling and make this information available to our DOT. And also INCORE project now is independent from National Institute of Standards and Technology. So we are getting engaged with US communities and trying to leverage this modeling in collaboration with US communities to understand how we can assist them with providing metrics and tools to improve their resilience. Also briefly, I'm going to just discuss, I believe there is also this growing opportunity in insurance and reinsurance industry. There are all these companies that they are interested on resilience. And for example, in Omaha, there are multiple companies that they are headquartered and they are developing their resilience teams. They are hiring in this area. So I believe this expertise for our graduate students that are attending this meeting could also benefit them in terms of their future careers. So here you can see some example of modeling vendors and companies that they are active in the insurance and reinsurance industry. As I mentioned earlier, I worked for Aon Impact Forecasting. And just to show you like two slides. So for example, when I was with Aon, we were interested to develop a model for Caribbean region. So we had more than 100,000 buildings insured in the region. And we were interested to understand what would be the implication of different type of seismic events, depending on the return period on the losses. For example, you can now estimate probable maximum loss, which is one of the metrics to price insurance and reinsurance products. And this is going to be the type of results that you might get. And obviously, there are all these challenges with uncertainty quantification, understanding if the model is representative of the actual catastrophe that may occur. Based on the results that we have seen, there are all these uncertainties with using this type of models to do regional level analysis. So I think I'm not going to have time to cover the next part of my presentation, which was focused on structural monitoring. So I'm going to just go back to my last slide to just summarize so what we learned from this presentation. Based on the experience that we have had in the past decade, we realized that enhancing resilience requires more than traditional approaches. We need to understand how we can bring emerging algorithms, multidisciplinary community data, bring insights, and develop adaptive frameworks that can reflect the unique needs, risk, and strengths of our communities. So this research that I discussed, I believe, is a step forward in community resilience science and understanding how we can couple local knowledge and develop platforms and tools that can help our communities to manage their assets and plan for their resilience. I didn't have time to discuss about my performance-based monitoring work, but I believe integrated use of advanced measurement devices for infrastructure monitoring with performance-based engineering and multidisciplinary resilience modeling provides a promising potential to make reliable assessment of our infrastructure and communities pre-event, during event, and post-event, and leverage this information for the purpose of enhancing our mitigation and recovery strategies, and ultimately achieve the promise of smart, resilient infrastructure and urban systems. So here I have included some of the collaborators that have contributed to this research from different disciplines. And I would like to also acknowledge the funding that we've received from different agencies in the United States, in the state of Nebraska, and also from University of Nebraska-Lincoln. And this is my lab, Smart Resilient Infrastructure and Urban Systems, my PhD and undergrad students. Some of the students, they are not with us anymore. So now we have new students. So this is a picture from about a year ago. And thank you so much. I hope this was interesting to you, and I'm more than happy to answer any questions that you may have.
Thank you so much, Milad. That was a fantastic presentation, and I hope this was extremely enlightening for all the listeners. So I will let the audience ask their questions first. if there are any. I already see that my colleague Dr. Shin has left a couple of questions for you. He had to leave for class, but he left the questions and he hopes that he'll get the answers from you on the YouTube link later. So do you want me to read the questions?
Please, yes. So I can see one comment. So thanks for the feedback. So it says, in the multidisciplinary community resilience modeling framework, how is the interdependency between water distribution system and the electric power system defined? I am wondering how it was quantified. So the way that we are characterizing the interdependency is by developing an interdependency matrix. So as soon as we obtain the inventory data for water distribution network and electric power network, so we look into the interdependencies that the systems offer. They have in terms of, for example, if you have a water tank, and then now we model the interdependency with, let's say, the substation. So now, so as soon as there is, let's say, a failure in the power network, for example, in one of the substations, so that basically give us the probability of exceedance for that node of, let's say, the power network. And now we can use that information to update probability of functionality of the node within the water network. And that's how we have implemented this. And because we are using this directed graph, so that basically also allows us to understand, so as soon as there is a drop in functionality of one node, so what would be the drop in the functionality of the other node by accounting for that dependency. I hope that answers the question. For restoration analysis, how did you quantify the recovery of water and power systems for resilience evaluation? What options were considered for the recovery of the system? So I would like to just mention, so the models that we are using, they are consistent with HAZES, specifically for water and power. And also one of the challenges that we had with Salt Lake City is they were not interested to share the power and water distribution network because there are all these challenges related to the attacks and security problems. So that's why we had to obtain the substation locations from the open source accessible platforms that are available. But unfortunately for the water network, we were not able to access those information. For Shelby County, Tennessee, we had extensive data available from years ago, and these are not the actual water and power network. So for example, for the water, so that's a simplified version of the water distribution network in Memphis, Tennessee. So what we are hoping is, so if we can make this type of platforms accessible to US communities, I think it would be really interesting to, and that's one of the efforts that we have, to basically try to make sure that the data would be secured in databases that are only available to the communities, because sometimes they may have some concerns even to share some of these data sets in the departments. For example, I heard this from one of my colleagues that even in LA Department of I think water management, so they have all these limitations and security levels to share these data sets. So I think what we need to do is I think we need to address that challenge and understand how we can plan for resilience, and then while we are very careful with those aspects of security.
All right, thank you. Arif has a question. Arif, you can unmute yourself and go for it.
Hello, can you hear my voice?
Yes, hi Arif.
Hello, Professor Roohi. As I'm going to work on community resilience during my future PhD studies, I'm going to ask about the data. The data that we should provide for developing community resilience functions. Is it possible for us that if we don't have a data set, as you mentioned, some institutions do not share their data, can we use synthetic data such as the data that have been developed by machine learning or finite element analysis, for example, past literature that have revealed some data about the communities and the damages that has happened to the community? Is it possible for us to use that, for example, in core or in other applications?
So if you're asking about thanks for the question. So if you're asking about the Incor, so Incor has this data service that you can upload your data set. And then, so the package is available from Python. You can install it locally. You can have access through the computing platform that we have at University of Illinois. So you can just register, sign up. And then as soon as you sign up and you have your account information, so you can connect to the space that is dedicated to you, and you can upload your inventory data sets, water, power, etc. But that's your role to create those data sets. So you can collaborate with the communities. You can create your own data sets. And there are also some publicly available data sets that they may lack some of the level of accuracy that you may expect. For example, for building structures, we have National Structure Inventory, NSI. We have bridge inventory data sets that are available for bridge network in the United States. But obviously for water and power, so that's challenging. So I've seen some efforts that to leverage geospatial analysis, machine learning to try to basically extract the location of power lines and then substations. Definitely, I think we need to improve on that regard to understand how we can develop those type of data sets. And I didn't discuss today. So one of my students, he's looking into this research of understanding what is the effect of data availability and accuracy in quantifying resilience metrics. So far we've realized when you take, let's say, the tax assessor data, which was the basis of all this analysis that I discussed today. For example, Salt Lake City, they shared very detailed building inventory data set with us. But let's say if I recreate the same model using a publicly available data set, you are going to see we are going to have this error. And specifically in the analysis that we are doing, sometimes less accuracy, like when you have low resolution in terms of the inventory data set, that may cause underestimation of the resilience metrics. And that could basically introduce all these errors when you quantify social impacts, economic impacts. And I think this is a major challenge for us to understand how we can characterize that uncertainty of quantifying resilience metrics given data availability. And that's one of the projects that we are working on right now. So we have 3 test beds for Salt Lake City, Utah, for Seaside, Oregon, and also Memphis, Tennessee. And they are located in different parts of the United States. They have different community sizes, different construction practices. So right now we are finishing up on a paper to basically show what's the effect of running this type of models using low resolution, publicly available data set. But what we realize is we need to do some level of data imputation and improve our building inventory data set to be able to produce the same level of accuracy, or maybe quantify the uncertainty bounds, like 1 plus minus sigma.
Thank you so much. That was so insightful. I think I will have the same issue for Joplin dataset. It's for tornado. That's what I'm going to work on. Thank you so much for the tip there.
Sure, my pleasure. If you have questions, send me an email. Happy to answer, and let's stay in contact.
Milad, do you have time for another question?
Yes, I do have time. I can stay.
All right. Saeed, you have a question. Please go for it.
Can you hear me?
Yes.
Oh, first of all, thank you so much for the amazing presentation. I have just one question. As you know, the aftershocks can significantly affect of recovery and resilience of structures. I want to know that, have you modeled the effect of aftershocks on recovery and resilience of this, your projects? Thank you.
Great question. We did not. So I was really hoping to show you my structural monitoring work. So in that case, I'm looking into like very detailed models of like FEM, fusing data from like sensors, and look into that process of cumulative structural damage. I believe it's very much important. So the models that we are using, they are not capable to account for that sequence of events. So we are just running one scenario, but that's a capability that we should add in the coming years. And also, I would like to also briefly, there are all this really exciting research going on as part of the INCORE project. So there was a dissertation at Colorado State. One of my colleagues, Mushtaba Harati, he looked into tsunami and earthquakes combined. And he was able to develop basically 3D fragility surfaces that now instead of having one intensity measure, you have two intensity measures, and look into that cumulative structural damage due to shake and also moment flux. So there are all those activities going on, and obviously, so this is a big problem to solve. So that was one of the reasons that I showed you that three-dimensional, multi-dimensional framework proposed by ASCE. I think we need to understand how we can focus on different modules. So every PhD student, every researcher solve one piece, and then we basically bring all those together. So this is not possible to just basically have like one group to solve this problem. So I think that makes it even more interesting. And I think the NIST Center was one of our our initial efforts to bring all these disciplines together. So when I started my postdoc, I was meeting with like economic scientists and social scientists and learning about all these terms that I had almost no idea. But after like 2-3 years of working with them, and we have made all this great progress. I didn't have time to show. For example, we were able to develop CG models using machine learning that basically learned that mapping from structural damage estimates to economic impacts. So now you don't even need an economist as soon as that model is implemented. So now basically you can learn that mapping between physical metrics and economic metrics. So as soon as you have your scenario or a real scenario, you can immediately get the economic metrics.
Okay, thank you so much.
You too, thanks.
Any other questions from the audience? All right, no more questions from the audience. I would like to ask one question, Milad, if
Yes,
that's
please.
okay. Yeah, so again, very exciting work. I've been following your work for some time now, so always love reading your papers. One of the questions was, you mentioned briefly right now that you are looking into replacing some of these economic models with machine learning agents, right? Do you think that will be enough in the long run, or do you think, I mean, we still need economists in there, and there will be more refined models of economics and social sciences that will be necessary to sort of help this whole in-core platform?
Definitely. So also we have made progress with automating the population dislocation model. So basically, so we need building inventory data for building structures, and we need housing inventory data for population dislocation analysis that has all those information about social and demographic information. So we have also automated the social module. So I think that facilitates modeling and analysis. But for economic model, I think these are very advanced models. So all those results that I showed you, I was working with like PhD students and postdocs and full professors of economists to develop those models. It takes time because they have to bring all these data sets to look into different sectors, and then also try to link our models to their models. So there has been all this progress, but I don't think we are there that we don't need an economist. I think like my understanding is we need to keep everyone at the loop, engineers, planners, social and economic scientists. And I think this idea of co-creation is also from the modeler side. So we need to co-create those models. But at the same time, I think we have this new opportunity to automate some of those algorithms. We need to understand where machine learning, AI can help us. And I think this is the next challenge. Like if you're a PhD student, look into AI-ready testbeds to understand how you can make this type of algorithms, AI-ready trained models. We have done some preliminary work. So one of my students looked into transportation network and developed a machine learning algorithm. We published in a conference paper, but we haven't published as a journal paper. But I'm open to collaboration. So hopefully after this meeting, we can continue our discussion with Debarshi, Dr. Sen, and also if there are others that they are interested. I think we need to collaborate and figure out these future challenges that we are going to have to bring with all these large language models. I think like we have a unique opportunity to process multimodal data. And I think this should be part of the future dissertation. So I did my PhD back in 2015 to 2019. So it was a different era compared to. So now I think we are much faster in processing data, learning, implementation, programming. I think the challenge moving forward is we need data for validation. Sometimes we don't have those data sets. One of the challenges is I think the input data sets, and I think we need to understand what level of data is required to be able to produce reliable result. And I think we are not there yet.
All right, thank you. No, yeah, I totally look forward to any collaborative work that we can do in the future. I'm sure we'll meet again in conferences and we'll talk more.
Yeah, sure.
All right. Dr. Tiwari, do you have any questions?
No, not a question. Thanks, Milad, for a nice presentation. Trust me, it was really enlightening presentation. And thanks for giving us heads up that you left some work which you want to present and you have not presented. So once we start the fall series next semester, you will be the first speaker. I'm
Happy
going to
to.
invite.
Yeah, I was hoping to discuss structural monitoring, but then I realized it's gonna be a lot of information to process.
Yeah,
And also we
I
didn't
think
have time.
let's give them a separate packages so that they can digest. So probably I think Dr. Sen, we should give an invitation even today.
Of course,
When we are
absolutely.
starting a fall series, you should be the first speaker and start like with the molecular dynamics or whatever you want to share. And that will be really good for everyone to start like a research in this particular area. So thanks for the presentation. Very nice presentation, very
I
informative.
appreciate your comment. Yeah, I was hoping to do a much better job, but I tried to just share what we have done, and then we had all these limitations on the time-wise. I'll stay in touch. Happy to have another meeting. We can have follow-up discussions, and also happy to present in the fall.
Thank you
All
so
right.
much. Thank
Thank
you
you
so
so
much.
much, Milad, again for the
You
wonderful
too.
presentation.
Great to just see you all, and thanks again for having me.
Sure.
Thank you.
Take
Just a
care.
quick announcement.
Yeah, sorry.
So this is our second last presentation for this series, and we are going to have our last presentation on the May 2nd. She is Professor Miriam is going to present. She's a associate professor at Purdue. She is going to talk about the material related research. So far, if you have understand, like we covered geotechnical engineering, we covered environmental, water, structural part, we've covered the transportation engineering, and we only left with the material science kind of a research. So now the Dr. Miriam is going to present on material science research. So I welcome you all for the next webinar, which is going to be happen on 2nd of May. Soon I'm going to release the posters and registration link, and you can join for that. Thank you so
And
much.
just to add, if you have missed today's seminar or any of the past seminars, please check out our YouTube channel. You'll be able to access all the seminars there.
Yep. Thank you.
All right. Thank you.
Thanks.
Take care,
Thanks.
everyone. Bye.
Bye-bye.
Thank you so much, Milad. Have a nice
You
day.
too. Thanks.